surface area spheres.
All right, in this set of notes, we're going to cover your surface area of a sphere. Usually when we talk about surface area versus volume, we tend to teach the surface area concepts first and then go into the volume because it's moving from 2 dimensions into 3 dimensions. In this case, we're going to do it in the opposite order because it ends up that if you know the formula for the volume of a sphere, for the volume of it, you can actually create the formula for the surface area of a sphere. There's a lot of explanation in what's going on here, and I do have some things that are sort of filled in, so you're not going to watch me write too much, but see if you can follow the thoughts. There's a little graphic here to help you with this. Okay, what we're going to do first is just kind of talk about the idea of volume. Remember, volume is all of the space that's inside of the figure. And we're going to say that it would be possible to break a sphere into a crazy number of pyramids that all wedge together, like this little picture here, that all wedge together and completely make the shape, right? You can even think of these lines that are shown here as like lines of latitude and longitude, which you've seen on the globe. And if we took all the lines of latitude and longitude and maybe even broke them into smaller increments on there, so they're not so large, you can break off these little regions of area. And then from those regions of area, if you extend from any of their vertices, you extend all the way to the center, you basically got yourself a pyramid. The only thing that would be wrong with that idea is that all of these things that would be the bases, let me color one in here, all these that would be the bases to your pyramids wouldn't actually be flat. And of course, if we were talking about Earth, but it's a sphere, if it were Earth, it would be all kinds of bumpy and stuff like that. So if we had a sphere though, even that would have some sort of curvature on there. But we kind of talked about this idea when we were calculating the areas of circles and said, if you just make a lot of pieces, then the roundness of it becomes something that we don't really notice anymore. So I start with the idea of like lines of latitude and longitude, but if you were to start to break those into the minutes and the seconds and whatever would follow after that, just break it down so tiny, you'd have these really skinny pyramids, but your bases would start to look flat. So one of the ideas here is that we're thinking that we have an infinite number of pyramids, Okay, now I'm going to start looking at some of the math here, and I hope you followed that. Okay, what is the volume of each pyramid? Well, here's the formula for the volume of a pyramid, right? It's 1/3 the area of the base, whether it would be a triangle shape, square shape, or whatever. And in our example, you can have like trapezoidal shapes if you're really thinking lines of latitude and longitude. You can get weird ones like that. So whatever the area of that base is, multiplied by the height. But a unique thing that we have here is that the heights of the pyramids are actually the radius because they all extend into the middle. So I'm going to take that formula for the volume of a pyramid and I'm just going to swap the h out with an r. Okay, next, we're going to write an expression that's going to represent the total volume of the sphere. Represent the total volume of the sphere, but in terms of adding all these pyramids up together. So the thing about it is, so you're going to see I just have a bunch of pyramids that are being added together. Oh, and the plus ellipsis here, ... You can probably put a little plus right there too. That means that there's going to be more in between there. So I don't just have 1, 2, 3 pyramids. I've actually got 1, 2, a billion, and then 1,000,000,001 pyramids. So you have a whole bunch that are in there. I'm just not going to list all of them. But the thing about the pyramids is that they're most likely going to have different base areas. See, again, if you go back to lines of latitude and longitude, which I hope you can imagine, you might have some square-like shapes. But as you're getting towards like the North Pole on there, they're going to actually become more of like a triangular shape. So all the bases are a little bit different here. And because they're different, I got to be careful that I'm not repeating this capital B value. So I'm going to call one of them B1. That could be the one that I colored pink here. B2 could be that one right there, like just colored blue. And then so on. Every different base is a different number. And that's what subscripts are for, is just to identify things that are slightly different. Well, you know what I mean from this case, the different bases that we see. But all of these still have a 1/3, and the radius is still the radius no matter what as you go through those. So remember that the dot, dot, dot means that there's a lot of information that could be in there. So we're imagining these pyramids all getting added together probably about 1 billion times to make this accurate. But ideally, it's infinite number of pyramids. Okay, next, we're going to take that expression, so hopefully you understood most of it. We're going to take that expression and we're going to set it equal to the formula that we already know to be true for volume of spheres, which is 4/3 pi r cubed. So these two sides need to be the same because they both represent volume. But now, after all the things I've talked about, you may have even forgotten what the whole point of this thing was, which is to figure out what's the surface area. To figure out that piece. Okay, so I'm going to look over here and remember that we have a bunch of repetition. There's a lot of things that are just the same. The only thing that's different from every one of these terms is going to be the capital B's. Their base sizes are different, but they all have a 1/3. They also all have an R. So I'm going to factor. I'm going to factor out the 1/3 and the R. So I'm going to show that here. The 1/3 has been pooled from each of these. Factoring is the opposite of distribution. So I'm going to divide out all the 1/3, but I'm also going to divide out all the R's. And that could have been done in a separate step, but I figured I'd just show you all at once here. You divide out both of those, and then it leaves in parentheses just the B1, the B2, 3, 4, 5, 6, all the way up to, oh, and I didn't mention this earlier, this is Bn, because I don't know the number that I'm going to get to, like if it's going to be 1 billion or 1 trillion, but just to whatever number it's going to end up being. Okay, so these things have been factored out, right? I haven't done anything on that side. The key thing is to really understand what that means. Okay, so I'm going to pause here for about 5, maybe 10 seconds, and I want you to try and think about this. These are all the bases of the pyramids, and try to think what all of these added together represents. Okay, did you come up with an answer to what you think all of these are when you add them together? Well, if I were to add that region plus this region plus that region plus that one plus that one plus that one plus that one all the way around the whole thing, you end up with the surface area. I'll call it SA here. You can end up with the surface area. So 4/3 pi r cubed is equal to 1/3 times the radius times the surface area. The volume is equal to 1/3 times the radius times the surface area. So if we're interested in figuring out what the surface area is, let's just solve for it. Let's remove these two things. All right, to get rid of the 1/3, you can divide by 1/3 or you can multiply by 3. But check it out. The other side also has a denominator of a 3. So those two can just get eliminated at the same time. Okay, so we got 4 pi r cubed is equal to r times our surface area. And then when you divide by r, you can just take that away from the r cubed that you've got there, and it drops down to r squared. And that is actually the formula for the surface area of any sphere. Okay, so for the notes, I've got one example, and I chose not to do just a basic question, not to just give you a picture of a sphere with the radius and then ask you to calculate the surface area, because all that would require you to do is just to take that radius and plug it in. And the worst I could do with that also would have been maybe give you a diameter that you cut in half and you plug in here. So let's make it a little bit more challenging. Yes, this is what we want. We want to find the surface area. But you don't get the radius, you get the volume, okay? So we know that 12,348 pi is going to be equal, well, that's the volume. So your volume formula, we're going to bring that in, which is going to be 4/3 pi r cubed, okay? And again, think, if I give you pi, if you're ever given pi in some tests, really SATs do this a lot. If you're given pi, what's the point of doing that? To make it cross out and to make everything else easier, to make this answer for radius to be a nice value that we can plug into that spot. That's the point of it. All right, so next I got that fraction to deal with again. The way that I think of it is I multiply this side, so there's no pi anymore. Multiply that side by 3, divide the whole thing by 4, and that's going to give me back r cubed. So let me grab a calculator. We got 12,348. We're going to times that by 3, divide it by 4, and we get 9,261 equal to r cubed. So if I take the cubic root of that last answer, I get 21. So not a number that we would have known to recognize, but we could have expected it to be a nice number since the pi was provided. Okay, so we can take that, move it over here. We get 4 times pi times 21 squared. 21 squared is 441. We'll go ahead and just multiply that by 4, which is going to get us to 1764 with pi. This is going to be surface area, which means that our units are meters squared. And then if you want to, you can go ahead and multiply pi by the 1764 to get a decimal approximation for it.